Good afternoon, all of you. So let us begin the topic on regression. Okay. Are you able to hear me? Just now I switched it on. Yeah, fine. So, okay. So everybody is able to hear me and you're able to get the slides? Okay. So regression is the class of algorithms where we try to make use of different variables which define the environment. So we say that the environment of a system is defined by a set of variables, dependent and independent. What is it that you want your system to predict, on the basis of which information? That is what is very important. So there are certain parameters which are independent, and then there is a variable which is dependent. So regression analysis deals with statistical processes that help in building a relationship among the variables. Okay. So what is this type of relationship? We will see. It can be a simple line that joins together all pieces of information in such a way that it optimizes uh, the kind of fit into the data, or it is a kind of curve fitting. We will see how it is done. So some applications of regression include predicting the price of a product in the future, to predict the score of a player in a team in the coming matches, to predict the number of dropouts in the village school, and every such prediction is possible on the basis of the observations over the period of time. So if you have to predict the price of the product in the future, then you have to understand what affects the price, which are those variables which we need to look at. So whether it is the requirement, the need, and the quality of the product, or it is different other kind of parameters which are defining the price. Similarly, to predict the score of a player in a team will record certain kinds of patterns of the game of all the players, or maybe the same player for whom you are going to predict this score. And based on those patterns, or based on those data collected over the time, we will be able to predict the score. Of course, the score information along with the data is necessary for us for the past. For future, we will not need the score. This is something which our system will be made to predict. But for the past experiences, the score along with certain other values which would have been recorded by the system would be required. Okay. And then in order to predict the number of dropouts in the village school, different parameters which affect this would be the requirement at home, a requirement in the agricultural field by the parents of these kids. There could be certain facilities which are not there in the school. There could be the food which is actually making them come to the school, and if it is not available, then there are likely chances that the school children will drop out. So how such conditions existed in the past, we should have the numerical data about it, and based on those sets of values for each observation, how many had dropped out. So if we collect these observations over a time, maybe every year or every 6 months, for over 10 years or maybe 5 years, then we can predict the dropouts based on the existing information, right? So we must understand that the environment is defined by the variables. Let us say these variables are x1, x2, x3, x4, etc. So there could be various different other parameters which can cause some dependence on this independent variable, on this dependent variable, of course, and have association with the output value. So the values of the variables are discrete and numerically represented. We will have examples afterwards. Okay. Yeah. So, is there anything Rajan is not able to hear the lectures? Am I audible, Rajan? Is there anyone else who is not able to listen to me? Okay, fine. So, I'll continue. So, the output y can be a number, a real number, or an integer. Fine. So, here we have to see that this output y must have its relationship built with the variables x1 to xn. So we try to understand the best possible equation for the function f that fits y equals f of x1, x2, x3, etc. You know how to write a function of a variable, a single variable. If you have, then you can always write it as a function of one variable x. And if we are representing this as y, then you can always say that y is equal to fx. So y equals fx is that function. And if you have multiple variables like x1 to xn that define the environment, then you will have to write it as y equals f of x1, x2, x3, xn. When you have a single variable in the environment that is independent, you say that it is a univariate data. When you have n such multiple variables that define this environment, we say that this is the multivariate data. We will talk about these a little later. So consider a single variable data for regression. Let us say there is one parameter x which has its effect on y. So y is a dependent variable and x is the independent variable. So we call this data univariate. So this uni stands for a single, and this single data is referring to the x value of this set of observations. So there are 5 observations where it was seen that whenever the environment variable x had value 1, then its corresponding value y was observed to be 1. When this value x was 5, then its environment variable, then its dependent variable y had its value 5, and I have taken a pretty straightforward set of values. So that as we go downwards in this table, 1, 1, 5, 5, 2, 2, by the time we are here in the third record of this information, we have built a complete relationship between x and y. We know that y is equal to x. That is how human brain generalizes the data very quickly. Of course, it will take some time for a computer to understand this relationship. We humans are good at generalization ability. When it comes to 4, we are sure that there is nothing else but x equals y. So even if you have this 3 equals 3 or not, we would have actually built this relationship as x, y equals x. And now if somebody wants to ask us what will be the value of y for value of x as, let us say, 20, we are sure that this value is going to be simply 20 because we have established this relationship as y equals x. Is this clear to all? Have you understood the significance of the data and its effect on the relationship between the two variables x and y? Y is dependent on x, so we are only looking at the values of x and its corresponding value of y. Yeah. So univariate data is the one where we have a single set of environment variable, single variable x, which has its effect on y, right? Had there been more variables like x1, x2, etc., then the data would be called as bivariate or multivariate data. We will have some examples here. So unsupervised regression is not existing basically. How can we say that regression is correct? You can always have a guess in the unsupervised way, right? Had we not been given this y value, which is actually causing a kind of supervision, we would not have been able to predict this relationship. And this is the output. Basically, regression has one output which needs to be predicted, right? So, whatever output needs to be predicted for future experiences, we must have our past experiences, the value of those outputs. So, basically, it is a supervised regression. Okay. So, machine learning is the class of algorithms. There is a question how regression is useful in machine learning. So basically regression is one of those techniques of machine learning. So machine learning gives us more usefulness in the form of its own algorithms. Regression is one such algorithm of learning, right? So basically machine learning has one subset of algorithms which are regression. And definitely this is going to give you an opportunity to see how machines learn. Okay, this is one form of learning. Another form of learning will be with the class data or the label data. Here it is not the label data, it is the function approximation kind of relationship, right? Am I able to satisfy this query, Deep? Regression is not 100% correct every time. It may have some errors. We will talk about these errors a little later. Okay. So Yashasvi, a supervised algorithm is one where we have a kind of supervision in the form of the observations output along with the set of our observations values. So whenever there is a supervised output, we always can control the parameters of the machine learning, right? This will be called as supervised. And let us go slowly. I will be picking up all the different forms one by one. You can ask your doubts in the domain of what we are discussing today, because there are certain things which are going to come now, like the accuracy of the regression, supervised classification, right? So many things will come slowly. When you are asking questions, you should ask questions right on the topic that we are discussing. Of course, towards the end, you can ask various different multiple questions of different types, right? So now we are moving ahead. When you recall learning, a machine with learning capability can predict about the new situation, seen or unseen, okay, using its past experience. So what is the past experience? It was seen, observed, maybe by human or by machine, that whenever this x value was 1, we observed that the y value was 1. That is what is the past experience. When the x value was 5, then the y value was 5. When the x value was 2, then the y value was 2. Of course, a very, very trivial relationship I have taken for the first example. So, what will be the unseen situation in this entire experience? Unseen would be to predict the y value for x equals 71. 71 is such value which the system has never seen. And for this, it is going to predict the value of y, and according to us, it should be equal to 71. All of us have been able to associate a kind of linear relationship between x and y. So, prediction is based on learning of the relationship between x and y. Then the training data is the collection of x-y pairs. When x is a single variable, then we say that it is a univariate relationship, univariate observation. And when it is having multiple values, multiple variables defining the input, then we say that it is multivariate data. And then testing data is simply the value of x for which value of y is required to be predicted. Okay. So when I plot these x and y values one by one, say 1, when x was 1, y was 1. When x was 5, so I might have taken this point plotted first, then the fifth point plotted second, and in the sequence, as we are seeing the data, we are plotting it. So plotting is not necessary all the time. We have mathematical ways to compute the relationship. Okay. Yeah, I will check for the background noise. Just please hold for some time. I will pause this and go. Yeah, so let us continue. So these points, when they're plotted, you can humanly check that there is still a line possible to pass through all the points, right? We will call this line the best fit curve for the data. This is we humans who can look at the points and we can find out which line will best suit. But then machine will have to compute its slope and the intercept. You know the equation of line? It is y equals mx plus c, right? All of you must have studied it in your school, where m is this slope, okay? You can say that m is the slope and c is the intercept, okay? Intercept on the y-axis, right? Are you sure it is correct? Yeah. So, and definitely the c is not taken as the intercept on the x-axis when I am defining y to be the dependent variable. So there are two variables, two parameters m and c that define the line. How best will you find this combination of these parameters? Humans are good at this, and the data was so simple that we were able to plan. Had there been a data which was difficult to understand, then, or maybe it was a multi-dimensional data, we would have had difficulty as humans. Okay, so here, of course, yeah, we are extrapolating the values, where if I'm having an unseen value of x as 71, I can predict it as y equals 71. How is it possible? Based on the data that has been used for training, that means these 5 points, we were able to find this m and c, right? This m and c such that no point is left out. This is where humans optimization skills worked well. But you can understand, whenever there is a term like best fit, or it goes through the maximum number of points, so the terms like maximum, minimum, best, all these correspond to a kind of optimization process behind. We will see how regression can be viewed as optimization problem later. So when y is fx, y equals x, right? So that is a thing which we developed. Now, if we have a slightly very different data set where I am not having corresponding to x equals 4, the value of y as 4, rather I am having y as 3. And when x was 3, I am not having the value of y as 3, now I am having it as 2. So there will be a difference. Now our equation of line will change. The equation that defines the prediction model, right? So what if the data to train the system changes slightly? The machine can still be made to learn, okay? So if I'm plotting these points, you can check out that there could be thousands of lines, or rather infinite number of lines that can pass through any combination of these points. But definitely there is no single line which passes through all the points. So the concept of finding a line that passes through all the lines is not possible. So which is still better? We will compromise with the term as best. It may not be the best. It may be passing, rather than through 5 points, it may be passing through 3 points or 4 points. It is a compromise on the accuracy, but we will get it. If at all we are particular about fitting the data with a line, we could have gone for fitting this data through a polynomial, okay? Yes, we can have curves, basically. So definitely we can have curve of which is a nature of polynomial. We can go for a single degree polynomial, or we can go for a 2-degree polynomial. And there could be several other ways to fit a suitable curve. But right now we are focusing on fitting a straight line. Even if this line doesn't pass through the 5 points, it may pass through 3 points or 2 points, right? So line is represented by parameters of slope and intercept that you have seen, and then machine must learn on its own which is the best fit, right? Here we are not going to tell it, but rather we are going to create a criteria for it to decide what is the best or what is the best possible line. Okay, so which line fits the best? You can tell this line, or somebody can say this line because it is also passing through 3 points, or somebody can say that this line passes through 2 points correctly. I can take this one. So there is always some kind of error associated with it, right? We will see how this error is computed, and then we automate a procedure to minimize that error which is associated with one line, and then we will try to find out the line which produces the minimum error. Okay, let us look at it. You can take this example where height was the independent parameter and weight was the dependent parameter. We are trying to understand the error. If we plot these in the two-dimensional space where x-axis will represent height in centimeter and y-axis will represent weight. Okay, so then you can have this set of points. Okay, the points will not have a single line passing through it, through all the points. This is one possibility. This is another possibility. Okay. So what is changing between the previous line and this line? Can somebody answer? How are these two lines different? These are appearing to be parallel. Yeah. So parallel lines will have the same slope. Yeah. Accuracy of line is the, of course, the different aspect. I'm talking about its parametric form. So the previous line was coming through a lower value of the y value. Yeah, intercept changes definitely. So all of you are answering intercept as its answer. What is changing is intercept. Now, this one is also having a different intercept, but the same slope maybe. This one, the new line, now the slope has also changed. Okay. So you will have infinite number of lines passing through some of these points. Which one should we prefer? Which one should we take? Right? This is a different line. Are you able to see the changes in the line? Yeah. So then you can check it. Another line was even a perpendicular one, which would have been the worst fit. So slope and intercept, instead of calling them M and C, we can call them W1 and W2. So one will represent slope, another will represent intercept. We are towards generalizing the representation of a line even for higher dimensional spaces. Right now we are working on the two-dimensional space where we are using univariate data and the other dimension is representing the output line. So in order to find a line that best fits the given data, we must find W1 and W2 in such a way that the sum of the squared error is minimum. How do we compute this squared error? We have an example. So let us just try to visualize this line and the points in the two-dimensional Cartesian coordinate plane. There are grids plotted. So what we are going to do is we are going to find out the distances of those points from the line. If it is directly on the line, then its distance from the line is 0, and then all together we are going to find out these points. You can understand that the y value of the dot which I have plotted with blue color is actually its actual output value. So blue dots, I must write it as blue dots y value. What is it? This is actually the actual output value. right? All of you agree with this? This is the actual output value of each data. Now, the point where the perpendicular on x-axis drawn from these points cuts or intersects the red line, corresponding to that point, whatever value of y we are getting, this is the predicted value. How do we view the predicted value? Once we have uh, obtained the model for the prediction, you will see that if you draw a perpendicular from a point, then wherever it cuts this red line, which is the regression line, the corresponding value of y is its predicted value, right? You know that the output is plotted on y axis. So predicted value is actually the uh, y value where I must write it as of the intersection point, right, on red line. Is it okay? What has happened? So are you not able to see the video? Anil, you have some difficulty. Can you restart? Yeah, others are getting the video, so please check it out. Yeah, you can restart your system and now you can get it. Fine. So others are getting it. So you can see this difference. The difference between the actual output value and the predicted value. You can see that there are certain lines where the difference between actual output and predicted value is positive, somewhere it is negative. Had we gone for just the sum of these differences, we would have actually nullified these differences, and then we would never have had known the kind of, you know, optimized value of this set of parameters. So what we are going to do is that we are taking these differences and then squaring them. I will get you a numerical to work on so that you understand these differences, and then you try to square them and add them up together to get you the squared error. Fine. Let us go to the next slide. Here you can see that I have computed the differences. Um, I'll show you. So you check out these lines. So I'm trying with the first data. So actual data minus predicted one. The very first point till this red line is the very first data and its unit is 1. I'm saying that it is 1. Then you have 0. So I have taken here in the sum of squares this 1 into 1, then 0. Then next time it is, sorry, this one has to be 1. Then there is minus 1, then it is minus 2, then it is 1. Like that you can keep doing. I think there is some fault here. So you can always check out whether it is minus or plus, but the square will make it always plus. So then this 2 square. So when you're going with the predicted value minus actual value, then it makes it plus. Right, so there are 3 minus values and 5 plus values, like that. So you get a kind of sum of squares as 13, right? So sum of squares is taken, then you go for the square root and then divided by the total number of observations, you get 0.45 as the squared mean error. Is this okay? Yeah, positive value is the difference between the predicted value minus actual value, right? So the third observation should have been here. We can correct it. I will upload the corrected one. So it should have been plus 1, right? Okay, but the actual amount is not changing, right? Yeah. Shubhanav, where is the difficulty? See, I'll just clean this thing, and I will write one expression. Say actual value, I'm writing y is the actual value, right? Actual value is the y value of the point, and y dash, let me write, or predicted value. I must write it as predicted value, right? So this is the predicted value, and as I mentioned earlier, that P is the corresponding y value where it has the intersection point on the red line. Okay, so what is this actual value minus predicted value? You have to take the square of this. Okay, for each point, you take the square of this for each point and then sum it up over all the observations. So there are 1, 2, 3, 4, 5, 6, 7, 8, 8 observations. If you compute for every such observation this value y minus p and take it to square, then you will get it correctly. I will check it out. Here it is 1, 1 is positive, and then 0. Then for the third one, so for the first observation it is +1. For the second observation it is 0. For the third observation it is +1. So in this third sum you can make it as +1 into +1. Then the fourth is -1. So this -1 is actually going in the fourth sum. So -1 into -1 will be the fourth term in the sum. Yes, predicted one has to be perpendicular on the red line. Yeah. So whatever you are drawing as a perpendicular towards the x-axis, it has to intersect the red line, and wherever it intersects, right, you have to take that y value. So 6 minus 4 for the fifth observation. 6 minus 4 is actually 2. That 2 you are going to look at and then sum it up. So the fifth observation, again you should correct. I think at the last moment I did not notice that this was the positive one. So +2 into +2, that is going to make it 4. Then the sixth observation is actually negative. So you can correct it. Sixth observation is negative, you correct it as -1 into -1. The seventh observation is -2. So again correct it. I could have taken it as p minus y square, so then it would have actually solved everything, but except for the first one. So I would actually correct it and upload. But by now I think you understand. Yeah. So 4 minus 6. Are you talking about the fifth observation? The fifth point, which is at 4, which is at 4. Okay. So fifth point, your actual value is 6 and your predicted value is 4. Prediction is what is through this red line. Okay. So I'm answering Biswajit's question. It is 6 minus 4 right here. The actual value minus predicted value. But since it is a square, there is no problem in taking p minus y square as well. Okay. Yeah, Vivek, you have a question. MSE is average deviation from an observed and estimated estimation. Yes, you call it as average deviation. What is the deviation? Standard deviation is actually something which is computed from the mean, but it is a deviation from the predicted value. Yeah. What is y minus p square, Harish? We are taking a square because we do not want to nullify the minus and the plus values of these errors which we are getting computed as y minus p. That is why in order to accumulate the overall quantum of error, we are going for a square. Otherwise we could have taken the absolute values. At least absolute values would not have nullified minus and plus effects. Is this clear? Any other doubts till now? Fine. So we are moving. Can we not take the value perpendicular to y-axis? We do not take it perpendicular to y-axis because y is that parameter which we are assuming as an output. Whichever is your output, we are taking things perpendicular to the data that defines the environment variables. So in this case, because y is an output, we are only taking the values perpendicular to x-axis. Okay. Yes, we can use mod instead of squaring it. That will also serve the purpose. Okay. For y minus p, you could have taken it as this mod of or absolute value, or I must say mod of y minus p. And mod of y minus p is also same as mod of p minus y. So any numeric absolute value you can take. Okay. So this way, if you are calculating the errors, then this is giving you one quantity. Whether this error is the minimum, had we changed the line based on its own intercept and slope, the entire quantum of error would have changed, right? Right now I am not typing anything, Tanveer. I just typed y minus p in modulus. That was the last. Fine. So yeah, total number of observations were 8. That is why in order to find the squared mean error, we are dividing it by 8. Okay, fine. So now you have seen one important thing, that there is an error which is associated, right? It is associated with one line, okay? Because if the line changes, the error will change. If your W and C changed, then the line will change. I can say that this line is defined. I must write it as line is defined by the parameters, right? Parameters M and C, and in place of M and C, we used W1 and W2. There are two parameters. I can call W1 as slope and W2 as intercept, or vice versa. So if I write vector, say W, as simply W1, W2, just defining these parameters of the line, then we can say that the error is a function of W. Is it not? I can say that error is a function of parameters W1 and W2. Are you able to see the changes from the form of the regression problem from X and Y forms to the form of E and W? Okay. Yeah. So is it visible now? Whatever I typed the last as error is a function of parameters W1 and W2. Fine. So if it is the parameter W1 and W2 that is affecting error, then I can take on this y-axis and visualize this error as a function of W. Assume that you had an interceptor 0. What is that condition when you have the interceptor 0? Can you tell? Which line will have intercept as 0? It is the line that passes through the origin, not the axis. It is the line that passes through the origin. So let me remove one parameter as intercept and just take only the slope as the necessary parameter. Then I have y equals wx. Okay. So my equation of line will be simply y equals wx in place of y equals mx. Okay. So what I am saying is that here I have an error which is dependent on this slope. If the slope of the line changes, in the previous slide also, you can see, I will remove this all annotations. You can see that if my line was something different, right? If my line was something different like this, then you would have had a different set of values which amounted to error, right? So the error amount would be more or less. It will be more. It will be more. Okay. So if my line changes, then the amount of error will be more, or it could be less. We do not know. So now we are visualizing this entire process of finding the best parameters that define the regression line. So now we are visualizing this entire concept as a optimization problem, where we have to reduce this error to the possible extent where we will get a corresponding W to minimum error. Do not get confused by this concept. I am just giving an overview of regression, how automatically the system will be able to find the best fit line, and how this is learning. The learning is through the data. Because it has the data, we are able to formulate some squared error. Yeah, has not yet come, Pranav, to HWX. Let me explain. So what you're seeing here is that the construction of the line through the parameters W, or let us say, slope and intercept. And slope and intercept will work only in the case of a two-dimensional data where you are able to visualize these. For a three-dimensional data, you will again have to worry about whether intercept is with respect to x-axis or y-axis or z-axis. So let us not get confused with three-dimensional data here. Yeah. So if a line is with intercept 0, it is not necessary the error will always be minimum. Anish, it is not always true. Even if intercept is 0, the error may be more, because then the line has gone away from the data. It is quite possible depending upon the data. Okay. So now we are visualizing that every such slope will have its corresponding error. So I must do some kind of writing here. Right. So let me draw this line from a point on the w-axis till the surface, and there are so many lines, right? And each line on the w-axis is having its corresponding W value. That means different slopes are corresponding to different error values. Okay. So different values of W correspond to different lines with different slopes, and different lines will correspond to different amount of error, which we computed in the previous example. So now we have a challenge to reach to a place where the error is minimum, and we will call it as global minima. That means this value of W, I must show you. Please wait. So this value of W is actually the one which we were looking for. So it is not coming properly. Let me just show you. Yeah, this line, this point of W on W axis is actually the one which is corresponding to the minimum error. So we have to start searching here and there and then find this parameter W. Otherwise, initially the system will not know what should be the slope of the line, and it has to search from the possible values of the slope the line which best fits, right? So W is the slope of the line. Okay. Yeah. Here in this example where I have taken y equals Wx, I have taken W as the slope. If we were talking about W1, W2, then one of these was slope and another was intercept. So there cannot be more than one slope, right? Because we are only looking for one line that fits the data. Okay. So for y equals x, it is that W is always 1. But who told that y equals x, y equal x is the line to the system? System must learn on its own. We are not going to tell and intervene as humans. We will only tell itself how to find its own W based on the data. So based on whatever data it has, it is going to compute the error for every possible W. Okay? Yeah. So Harish, you have a doubt. What is EW? E is the error, and based on the same lines, when we write f of x, right? This means f is a function of x. That means whenever x will change, the value of fx will change. Okay. If I represent y equals fx, that means the value of y changes whenever x changes. So on the similar lines, if I am writing that E is a function of W, let me represent it as something like Z, right? If I'm writing it like this, then what does it mean? Whenever W will change, the value of Z will change, and Z is nothing but the error. So W is the slope. Whenever the slope will change, the error will change, right? So EW is clear, okay? Now I'll take up just please do not put your questions very fast. Otherwise, things scroll up and it is very difficult then to see the questions one by one. I will take up. So EW is the sum of squared error, right? So we have computed it as the sum of squared error, and of course we have taken the average on that, right? Square root and then average. You can plot anything. You can even plot just the sum of squared error, or you can plot square root of sum of squared error divided by the number of observations. But you will get the similar type of surface. Okay. So yeah. So those who are joining back the session late, I will request them to join the sessions in time, because then it will be very, very difficult for me to go back and retrieve what all you missed, right? So yeah, some specific doubts I can clarify right now, but next time you can make sure that you join in time. Okay. So please do not ask questions like different things in between. Um, bit sessions will be uploaded quite soon. So this was discussed in the yesterday's class. Please, okay. So sessions are uploaded as and when they get ready. So there are some technicality. They may take 1 day time or 2 days time or maybe few hours. They upload it. So you have to keep checking your Takshila portal. They get uploaded. Like yesterday, it was uploaded by evening 6, 7 o'clock, right? But I would prefer that your questions should be more specific to the lecture that we are having here. And towards the end of the lecture, you can ask any other things which is not related to today's agenda. Fine. So now, is this okay, Vishal? Right? So please try to see that you do not miss anything, or else every video will be also available for you to pick up. Okay. Um, So right now we are focusing on slope, not on intercept, because I wanted you to visualize the relationship between only one parameter and the error. The parameter W, which is the slope that defines the line, and the error. Had these been two parameters, slope and intercept, then you would have had to visualize a two-dimensional plane of W1, W2 and a two-dimensional surface, right? So we will be having those things a little later. Okay, the slide which you are showing is a parabola which cannot be a straight line. Yes, Yashasvi, this is not the straight line which we were discussing right now. This is not, the straight line is different, right? A straight line is one. Along with this, you have understood that this straight line has its own slope, which we are calling as W. Is it okay? Similarly, if we have this line with this slope and zero intercept, we understood the process of computing the error, right? So error is associated with this W and we computed it as E. Since this error is actually heavily dependent on this line's slope, we are calling it as EW. So for one line, we have one W. For one W, we have one error value, right? Had this line been a different one, like this would have had a different slope, maybe W dash, and a different error. That error would be something E dash, maybe some other value. So for each line, there is a pair of values as W and EW, right? When you will plot it on W and EW plane, you will not get a straight line. You will get some different relationship. It is not even hyperbola or parabola. It can be as different as this. It could have been like this, a different surface. We do not know. Rather, we do not need to plot it when we are doing the regression. But this is for the visualization of our own understanding and own data. So had this been like this, that means for one corresponding W, there is one error, and we are looking for that line this defined by a particular W which has the minimum error. This is what we are going to find. So definitely all the lines which have different slopes will converge to the kind of point that is here. Am I right, Yashasvi? So now we will slowly go through the hypothesis concept. We will say that each line is defined as HWX. X is the variable on which we are going to find the corresponding Y value. And the function f is defined as h of w. It is actually this w which is the most optimal one, right? We will have a complete program for this, and it will give you more clarity when you will do it on your own, right? So we will have multiple slopes and each line some error. So multiple slopes are not for one line. Different slopes are for different lines. One line has one slope, okay? So, and then corresponding to each slope, we are computing the sum of squared errors, and then we are plotting it on this E axis. Biswajit, is it okay? So there are no multiple slopes, okay? So it can be squared mean error, or it could be the squared deviation or sum of squared error. Anything you can plot. Fine. So slope is with reference to x-axis in this case, right? So shall we proceed? Okay. Now comes the multivariate regression. You had the visualization of the single dimensional, single variable regression, which we call as univariate. Now we are coming to multivariate regression. The similar concepts will extend. Only thing is our visualization will not be for more than 3-dimensional spaces. This is the limitation of humans. We cannot visualize anything beyond 3 dimensions. Of course, mathematically it is possible to handle even larger dimensions. So why it is, yes, what is your full name? Sri K I am getting as your nickname. Sri K. Can you tell me your full name? Yeah, Shrikant. Why is the slope in the, it is the slope in the x-axis. It is, it can't be just x. No, I'm not getting Shrikant. What does it mean? The slope is of the line with respect to the x-axis, right? You might have studied in your school that if you have this line drawn on the x-axis and x and y plane, then its slope is actually this angle, the angle which it makes from the x-axis. Okay. So parabola doesn't exist anywhere. We did not ever discuss parabola. It is just the surface which we are having plotted here. So parabola I am not discussing. Parabola is not going to have any concern about its own slope, right? So basically this slope of the line is plotted here on W-axis. And correspondingly, we have the error computed that we are plotting on this E-axis, which is actually the Y-axis. It is the two-dimensional plane. Okay. So find various slopes for given data. Definitely, yes. You are computing the slopes and then defining the lines, and then computing the sum of the squared errors, right? And in the squared mean error, you are having different lines with different W's. Yeah. Fine. So we go ahead with this discussion. So the regression model builds a relationship between y and x such that y equals w, y equals f of x1, x2, x3, etc. And then the regression line is an n-dimensional line. So the equation of this regression line is w1 x1 plus w2 x2 plus wn xn. So yeah, I'm breaking here for 5–10 minutes for technical reasons, and then after 5 minutes or so, I will join back.